organizer for organizing such
Above all, Apramino, it is here.
a great
Yes.
workshop. Yeah. And for forcing us to work so hard. Okay, so I want to try to connect loose ends of these discussions I had. And the first thing I want to discuss briefly is I postponed it from last time because I wanted to use Arvid's lecture to do this. You remember from the last talk, we constructed this standard Harishchandra sheaves, and they have unique irreducible subs. And these unique irreducible subs have very mysterious structure. They are defined in a very simple way, but on the other hand, we have no idea how they look like. But still, for standard Harishchandra sheaves, situation is better, and there is a duality theorem. You do Heck, Schmid, Wolf, and myself, which says that, first of all, lambda is arbitrary. So it works for all chambers, and then it calculates the cohomology of standard Harishchandra sheaves. Actually, of their Harishchandra dual, this check denotes Harishchandra dual. So you take algebraic dual with dual action of the group K and Lie algebra G, and take K finite vectors. And you get Harishchandra dual. And then this is equal S minus P C, I have to explain all the notation, R plus. You check tensor with P star of omega x. So first of all, S is like in Arden's talk, this is the dimension of the Lie algebra K intersected to the Lie algebra N. Of course, I'm doing this in the wrong order, that didn't define what any. So first of all, I have this orbit Q. Let me try to draw a picture. I pick a point, the Borel, in the orbit. As I mentioned, this Borel contains a Cartan stable under Cartan involution. So this is our C. R plus is a positive root system in roots of GC. So this R plus determines a Borel. B is C plus, say, N, where N is spanned by positive roots, subspaces corresponding to X. This C, on the other hand, since it's, so now this explains S, and C is, again, as in Arden's talk, direct sum of toroidal part and split part, and we have an algebraic group T, which is centralizer of C in K. And this gives me a Borel and an algebraic group. They both act by construction on geometric fiber of tau, and this is our module U, which is a BT module, and this is its contragradient dual module, and this is the fiber of the canonical bundle. So this is basically 2 rho for a choice of rho. So this is nothing else than a cohomologically induced representation from the pair BT to the pair GK. So this theorem calculates cohomology in terms of cohomological induction and allows to go from the module picture to cohomological induction picture. Of course, one peculiar aspect of this is that our B, in Arvin-Stokes, B was chosen to be theta stable. Here, B is completely arbitrary. It doesn't make any difference in the theory. And I mean, you can, from the theorem, you can see some simple facts, some vanishing theorems. For example, some of them are really dumb, like cohomology doesn't live in negative degrees. This gives you a vanishing theorem for cohomological induction, which is not completely trivial, although it's, I think, more or less useless. But David Vaughan was very happy a number of years ago when he managed to find an algebraic proof of this without invoking this deep fact about sheaf cohomology. I mean that cohomology is 0 below. Yeah.
Lambda is arbitrary.
Yeah.
No regularity.
No regularity. Completely arbitrary. So, related to our question, let me point out that, so this was mentioned in passing in his question. If we assume that we are in Borel-Weil-Bott situation, so the group acts transitively, so this is a line bundle, and as he mentioned, this also gives basically calculation of finite dimensional representations. If you compare this statement, this is nothing else than Serre duality in this special case. So in a way, you get a generalization of Serre duality, but you have 2 different cohomology theories besides. So this tells us that these standard modules are not as mysterious as cooperation. Didn't want to show this. Another remark I want to make is related to Gus.
Here, everything is arbitrary other than the carbon, right? I mean,
basically, the arbitrarity is in lambda. You can be in any chamber you want. And then, of course, if you are outside of anti-dominance range, then you have higher cohomologies, and then this just gives you some of these cohomologically induced modules in standard degrees.
it's in the same language of the next language, that T and I think there is some KO because one would be having the action of the sigma as just identity and the other would be by minus identity. I mean, 1 and minus 1.
Yeah. This is just these are the eigenspaces. Sigma is Cartanian Milicic restricted to C, and this is plus and minus eigenspace. Yes. Okay, now let me discuss something totally different but related. Let's look at Hasselmann's subrepresentation. Theorem. So I look at my Lie group G naught and I write the Iwasawa decomposition of it. And now use this n over there, but at the moment I won't use duality theorem. In this case, I can look at the minimal parabolic P naught, which is just M naught, A naught, N naught. And M is compact, so I can take an irreducible representation, omega, finite dimensional representation of some space U, and I can take a character of A naught, which is just e to the sum lambda apply to log of A, where lambda is in dual of complexify Lie algebra of A naught. And then I can construct induced representation of this representation of the parabolic, which is omega on M naught, this character on A naught, and trivial on N. So this is in omega. Oh, okay. Well, let me just put nu here. Nu. So this is the minimal principal series. Representation. So the elements of this space are the functions which look like fp g, which is equal to representation omega, say tensor ni, I mean this represent just omega ni, applied to p, f g. Again, I won't specify for a moment in what class of functions I'm dealing with. And the group G acts on this induced representation by right translation. So the point is that if I take, say, smooth functions on G with this property, or say something else, I always get the same k-finite vectors, and I get the corresponding Harshchandra module. I don't want to be specific about this because using, again, cohomological induction for the pair, going from the pair P M naught, where P is complexified Lie algebra P, M naught is this M naught from minimal parabolic, you get this cohomologically induced representations. In this case, the functor of cohomological induction is exact. Higher derived functors is zero, and in 0 degree, you just get Harshchandra module of this representation. So we don't care about, actually, I'm interested in the corresponding Harshchandra modules and not the group representations at the moment. And then, so what is the problem? So this, I will be vague and use the same notation for this functor for a moment. So this induction goes from N, P, N naught into N, G, K. And there is, so what is known as Casamance Frobenius reciprocity, which is a special case of the formula Arvind wrote this morning, which says that Hom and Casaman proved it by trying to find real analog of Jacquet's reciprocity for p-adic groups. So Hom in the category of GK modules of B and this induced module is Hom in the category of P and naught modules, 0 and homology, this is Iwasawa and V and omega. So this is, let me remind you, that this is just V mod N V, because I will slightly modify this construction in a moment. And the important thing to mention that there is so-called Osborn's lemma, which says that if V is finitely generated as a module over enveloping algebra of U of G, so for example, if V is our Harishchandra module, then it is also finitely generated over enveloping algebra of N. This follows from ZG finiteness and finite generation. So in general, this zero N homology is finite dimensional. So, if it's finite dimensional, we can lift the representation. It is also, a module or for P, and we can lift it to finite dimensional representation of P, and then I can take an irreducible quotient of this finite dimensional representation, and I will get a representation which is trivial on N, it's a character on A, and irreducible representation of N naught. I put it here, and then I have a non-trivial homomorphism here, which gives me the map from V into induced representation. Under a condition that this zero N homology is non-zero. So if I know that this is non-zero, then I have an embedding of the irreducible Harishchandra module V in this induced representation. So this is a strengthening of Harishchandra's subquotient theorem, which states a slightly weaker statement that id omega nu is a finite length. Okay, we discussed this in detail, but that any irreducible Harishchandra module is a subquotient of some principal series representation.
Sir?
Yeah.
So, the capital V is the irreducible GK model that you started with? The capital V is the irreducible GK model that you started with?
Yeah, I'm assuming at the moment in this discussion that V is irreducible, but of course the statement has nothing to do with irreducibility. I'm just, in this case, you can see that this is an embedding.
This
not is an adjoint of the induction function.
Yes, yes. So this is again one easy adjointness formula.
So this H naught, I mean, we are saying that it would be equals to V.
Now, Lie algebra, homology, upon homology, you can find things like this, and these are the right functors of this. So, what else we get knowing this fact? If we know this, then we know that since by Frobenius reciprocity, the K multiplicity is here, this representation as a representation of K is a representation induced from compact group M naught to K. So Frobenius reciprocity tells us what the multiplicities are, and we see that multiplicities are finite, and we see that V is admissible. So this is one way to prove admissibility of irreducible Harish-Chandra modules and then all Harish-Chandra modules since they are finite length. This is first remark. Second remark is from Frobenius reciprocity, you also have an upper bound for the dimension of isotypic subspaces. And this is the upper bound Harish-Chandra uses to prove existence of characters, the characters of distributions. So everything what we need for that proof is in this.
So in the general manner, we look at the induction counter, the adjoint counter with the restriction. So in the classes it's here
It is in a way a restriction if you look at its representation of P, but then because Mx is trivial here, you can cut this out. So you're right, but you see the problem in this case, V is infinite dimensional, and we know that by Osborn's lemma that this is finite dimensional. You're right. Yes. Okay, so one way so now I want to discuss this question because this was at least at some point a critical questions to discuss. First of all, Harish-Chandra at the beginning, I think in all the papers assumed implicitly that there exists a group representation with corresponding Harish-Chandra module, so that matrix coefficients exist, as you will see at the moment. Using existence of matrix coefficients, you can prove that that H naught of NV is non-zero. So this is the question. I will discuss in a moment how this, what is the connection of this with matrix coefficients, but let me point out that if you have Harish-Chandra subquotient theorem, which it was proved by Lepovsky, I think in 80s, without the assumption that matrix coefficients exist, then you know that the irreducible Harish-Chandra module is a subquotient of a Harish-Chandra module coming from representation of G, so you know that matrix coefficients exist. So in this way, this is another way to prove existence of matrix coefficients. But let me formulate what I mean by this. So if I have a Harish-Chandra module B, I can take its it's Harishchandra dual. So this is a GK module, of course, and this guy is also a GK module. So therefore, I can form a tensor product, and let me just see how I want to do this. Check tensor over CBB, and I can view it as a G cross G, K cross K module with one copier GX here, the other on the other variable. So, and and then I can look at C infinity of G, and I have a left and right regular action on C infinity of G, and I call this map a matrix coefficient map if it is equivariant with respect to this action, and C of B check tensor B is at the identity is B twiddle evaluated on B. So again, using these tricks we discussed, first of all, using an ellipticity argument, you can show that matrix coefficients are always real analytic functions, and then you see that if they exist, they are unique. Say if the group is connected, but you don't need this because disconnected is for Harishchandra groups of Harishchandra pairs is included in K from Taylor series. You can, which are given by the action of the Lie algebra, you get uniqueness, because since the Lie algebra acts, you can write a Taylor series of identity, and this gives you the uniqueness. So the question is, and if you have matrix coefficients, then of course you can construct the character of Harishchandra module by standard summation of diagonal terms. So now let me do a construction or calculation with these matrix coefficients. Okay, maybe I can start here. Just to give you the idea what is happening if this question has a negative answer. So let's assume that B is equal to NB. And I will do calculation, which is kind of like physicists often do. So don't complain immediately. I will make it precise a little bit later. So if I have a situation like this, to make calculation make sense, I will write real matrix coefficients, like I have a group representation, but everything can be written in this language without too much effort. So I look at the matrix coefficient. So B twiddle pi A B. A is in our A naught in Iwasawa decomposition, and because of Cartan decomposition, we know to understand the asymptotic of matrix coefficients. When you go to infinity, it's enough to understand what is going on A naught. So I take vector V, and I can write the vector V as some since this condition holds, pi ci vi, where ci are in some root subspaces with respect to A, so these are just real roots, alpha I, and I plug this in my formula, and then I get that this is V twiddle of each, let's say V check. Let's have checks here, and then sum. So I pull this pi A over this, so I will get pi of odd A ci, and then I have pi A V. Now,
VI.
VI, yes, thank you. So now these are in root spaces, so these are just e to, let's see what is alpha I A ci, and I can pull these numbers out, and let's see, this also check is missing here, and I get that this is the sum of e to alpha I A, and then I can move this pi ci to the second variable, because this is contra-green in the representation. I will get minus pi ci by check, ci v check, and then pi a v I. Now, we are going to look at asymptotic behavior along the negative chamber. So when these roots alpha I on log of A tend to minus infinity. So these guys are going to zero. So to have this equality, some of these matrix coefficients have to grow faster than this. Does this make sense? I mean, I am just using this to motivate Harishchandra expansions. In Harishchandra expansions, this will be completely clear. Now I'm just waving hand a bit. In this way, you can produce matrix coefficients which grow faster, faster, and faster if this condition holds. So the conclusion is that this cannot be true, and H naught of NV is non-zero. So this proves that existence of matrix coefficients is essentially equivalent to the non-vanishing of zero and homology. And now, before discussing Harishchandra expansion, I want to make another remark, because I still have in mind the Pender's list, and I want to check various things. And sometimes this will be really minimal, but let me, so if you believe in this thing, then you see that irreducible modules embed into induced representations. So Casamas theorem. So you can ask, what happens if your module is not irreducible So V is just a Harishchandra. Then you can modify this construction and consider these spaces. And there are also modules for, they're finite dimensional because of Osborn lemma, and it doesn't act trivially on them, but this doesn't make any difference, and we can consider them as PM naught modules, and we can prove in the same way this Frobenius type reciprocity, and we get, so this is related to your remark that about restriction. So we get home GK of V into use of V and K V is non-trivial. But now a small analysis of this implies that if I take sufficiently large K, then actually V will embed in V and K. So any Harishchandra module sits inside this induced module.
For K large, and
What? Okay. We know that the first one won't be the zero, and then we can continue this, and we get more since this. Remember here, this guy was quotient of this guy, so this guy is quotient. There are such maps, but if you look at this, you can make K large enough so that the map here you get from reciprocity is injected.
So I'm just saying that if K is large enough, then n K by itself would be zero.
It's not general thing.
No.
Okay.
Okay. So now let's go back and think about this. I can consider now that we look at smooth induction. So in our definition of induced representation, I take smooth functions on the group in this finite dimensional space which transform under this. This space of smooth functions has a natural locally convex topology by convergence of functions of their derivatives, and this is the Frechet space, and V embeds into this Frechet space induced representation. You can look at a closure of V in this space, and this will be a Frechet space invariant in the group action, so this will be a C infinity completion of V. Of course, this C infinity completion depends on the choice of embedding. I mean, I was here taking an explicit embedding, but this is the Kasseman-Wallach completion, and what they proved using a lot of technical trickery, that this is actually functor. It goes from Harishchandra modules into this category of representations on a class of topological vector spaces with particular properties. And then, of course, taking a Harishchandra module for such a representation is the quasi-inverse of this. This is an equivalence of categories.
They're all precious spaces.
Yeah.
They're all precious spaces.
Yeah, yeah, but of course there are other functorial completions. There are these maximum and minimal functorial completions studied by Kashiwara and Schmidt, and so in a way this is one which is good for certain applications, and for some other applications, you have to use others. There is an announcement of Kashiwara and Schmidt, which does this in a very elegant way, using some fancy homological algebra and some results of Kashiwara. But I doubt that the details will be ever published. Because the proof seems to be quite long, but if you're interested in these results, I think this paper of Kashiwara and Schmidt is very inspiring related to this question. Okay, so now I am really pressed for time. So now I want to use this picture. So I want to discuss briefly Harishchandra's expansion of matrix coefficients. In the case of SL2, we want, as I mentioned here, we want to understand behavior of matrix coefficients on A norm. And in SL2, I take the positive root map, which sends this matrix to A square. So our A maps in the positive, on positive real line. This is called a point minus infinity. And if we write down Casimir for a matrix operator and how it acts on matrix coefficients corresponding to K types N and M. So I think this is the same notation, should be the same notation as in SL2 lectures. You get this formula, which just looks threatening. But if you look at it carefully, you see that there are three regular singular points at 0, at 1, and at infinity. So therefore, you can write down using classical Frobenius, the Fuchs-Frobenius method, you can write solutions of these equations. You look at the initial equation and you have z to the solution of the initial equation times power series, and you have two solutions of initial equation in general. If their difference is an integer, then you can have also log terms. But basically, you have these expansions, and then you can look in the ordering, say, of these with respect to integral differences of these leading exponents. Exponents you can define minimal leading exponents, which are blowing up the fastest approaching 0, and they give us the growth of matrix coefficients. Harishchandra tried to do the same in general. Any questions? And he wrote 2 papers. One paper is explaining the action of the center of enveloping algebra related to this formula for SL2. So basically, this is what Helgason calls calculating radial parts. And the second paper was the analog of generalizing Frobenius' classical theory of solving differential equations using power series. Unfortunately, he made, I'm sure he was completely aware of what is happening in the case of SL2, but he had chosen Lie algebra coordinates to work on it. So the infinity was not easily visible. So if you look at this type of coordinate, say in the case of A2, then say our A is this quadrant. So one simple root gives you this, one gives you that, and the sum of simple roots, say for A2, gives you this. And this is the neighborhood of minus infinity. And you can look at differential equations for the matrix coefficients on a product of these punctured disks. And if you look at Harishchandra's calculations, you see that solutions of these differential equations given by the center can be written in a similar fashion. There are of the type Zi partial I of, say, pi to f times say f times a matrix value. This is let's see. Anyway, you get a first order system that possibly you have Zi partial i's, some coordinates. So you have simple singularities along these hyperplanes. And so instead of, I could explain you the proof in a few minutes, but maybe since it's late, it's better to tell you the story around this. So Kasselman was reading Delini's book on differential equations with regular singularities, his lecture notes. And he realized that Delini there treats this case with normal crossings. And basically, just by doing one-dimensional tricks in CN, looking at a monodromy around each coordinate hyperplane, and then playing the same game and restricting things to slices using the moderate growth section there and the classical argument that this forces the fundamental matrix to multiply by the inverse of monodromy to have moderate growth, and then using their category argument to see that actually you can replace functions with singularities along coordinate hyperplanes in power series, which on this product of the disks. And these are Harishchandra expansions. I mean, and this is explained in this paper of Kassaman, and myself. I mean, I asked Harishchandra if I could, before that, if I could see his manuscript, and he said, of course, and gave me the manuscript, and then came back after, I don't know, a few weeks, and he said, did you read this? And I said, yes, and he was kind of surprised that I actually read this, and he said, you know, I asked Hermander to help me with this, but he showed no interest. So, and if you look at his proof, I think he had all the right ideas, but they are kind of hidden because you don't see monodramatic. So there are some linear algebra arguments which I was kind of having a hard time to figure out what was exactly he thinking doing this. Anyway, so in general, you get the same picture. You get some multi-dimensional power series with some, say, z to the multi-index lambda log to multi-index m to z and some polynomials. Power series, sorry, it's too late. And so these are Harishchandra expansions of matrix coefficients. You can introduce integral partial order on, say, product of these lambda, on sum of lambdas and powers in this series, and then you will have finitely many leading terms, and then they determine the growth of your matrix coefficients, and these are the leading exponents of the representation. If you go through this argument, then you see, knowing this, that you can easily conclude that leading exponents of matrix coefficients, their initial equation is related to the action of the center of the enveloping algebra. So there are finitely many of them, and they come from, say, the action of the center. So they're uniform for all matrix coefficients. But any leading exponent by this argument over there will be a weight of zero n homology. But, so, after reading this Harishchandra's manuscript, I realized that actually this is what we get from connection between zero n homology and asymptotics. But I needed something more precise, and in p-adic case, if you look at Jacquet modules for various Levy factors, basically these sets are equal. Leading exponents are essentially the things which appear in zero n homology, and this is one of the results in Bill's Kassaman's p-adic manuscript. So I talked to Schmidt, and Schmidt said, oh, there is an example that there are weights of zero n homology which do not correspond to leading exponents in some discrete series representation, right? So I try to understand what's going on, and then I think this is the theorem Dipendra mentioned in my homework, Kassaman and Milicic. We determined that leading exponents are the lowest weights in zero n homology with respect to the integral order, the weights which grow the fastest. So if you calculate n homology, you know precisely what are the leading exponents of your representation, so you can see how your representation behaves at infinity. So, for example, if you want to determine if your representation is discrete series, you do not have to do any analysis. You just calculate n homology. What is my time?
Another few minutes.
Okay, perfect. So this is what I need. I just wanted to wrap up with some comments. So if our Iwasawa n sits inside n of a Borel, and because of Iwasawa decomposition, this n is an open orbit because an is in the Borel and then k, and so the tangent space of the orbit is the tangent space to the flag ground. So, and there is only one open orbit. N homology component corresponding to some weight is you get by taking corresponding localization. So you have, remember at the beginning, you have all these Lie group elements. For each element you can localize, and the component now, since I have no time, I won't worry about row shifts of the localization at that chamber. If you look at the geometric fiber, then actually there is a spectral sequence which gives you this component in n homology of your original module. So if you are an open orbit and your module is holonomic, then it is either a locally free all module or zero. So geometric fiber has no derived functors, so this is just the fiber of localization. And so to find the leading exponents from geometry, you have to figure out which localizations. I described the functor geometrically only in the tutoring session, supported on the full flag right. There is a technique used by Bernstein to prove that generically H naught of n is non-zero for any modular or enveloping algebra. You choose the technique that when you flip by intertwining functor across the simple wall, your support can increase only by 1. And so in the paper with Heck, Schmidt, and Wolf, we studied this process carefully, and we determined how the leading exponents of this Harshchandra sheaves, so some bounds for them. And from this you can see that discrete series can exist only if you have compact Cartan, and they have to be d-module attached to closed orbits, because otherwise it wouldn't be square integral. For tempered representations, the condition is you can take, like from SO2, standard module for any orbit and any sigma stable Cartan in there, but condition is that lambda is imaginary on the A part of the Cartan, which corresponds to unitary induction. And in this case, the LQ tau is equal to IQ tau, so unique irreducible, the standard module is irreducible. And this is why tempered representations are so simple in comparison with, say, Langland's representations. I mean, also these tricks can be used to prove Langland's classification and also classification of Wogan and Zuckerman using cohomological induction. But now I think dimension. Right?